Hello guys and welcome to the MATLAB and Simulink robotics arena. In the last video, I showed you guys how to do inverse kinematics for manipulator control, and today Sebastian is going to be taking over that work and showing us some different type of robot manipulator algorithms. Hey Sebastian, how are you?
Hey, good. You?
Pretty good.
Nice. Yeah, thanks for the introduction. So, yeah, we have a pretty fun agenda to follow up from the previous video. One thing we'll let you know is if you have not seen the previous video, that is linked in the description below. Otherwise, we will do a quick recap. So, what we talk about today is, first of all, what is the problem that we're trying to solve? And then we'll dig deeper into a couple of things, namely this notion of what is inverse kinematics versus inverse dynamics, which is going to be an important thing for today's video. And then also talk about designing controllers for the joints of a robot manipulator. Most of the time will be spent on the software, so that's what makes today extra fun. And we'll, as always, we'll wrap it up with some key takeaways. In the previous video, we had this robot arm here, which is the Robotics Open Manipulator chain. And what we did is we created a couple of tasks, including, grasping an object and moving it through a set of waypoints and even tracking its position to grab it. So we're going to continue with those same requirements, but now we're adding an extra layer of complexity, which has to do with actually controlling the joints.
Thanks
Yeah,
Sebastian. And one more thing, if you guys remember correctly, we did all of this in Simscape Multibody, and we used the option of using motion actuation for the joints. So that is why we were able to do this with just the position for the joints last time. This time we're going to be actually looking at some more motor performance.
yeah. So this is ultimately the goal that we're trying to solve, right? You want to move the robot gripper or the end effector to a particular position. In the last part, we talked about kinematics, namely the forward and the inverse kinematics. And that's what maps you from the actual angles or displacements of the joints to the position of the end effector. So forward dynamics is the easy one to solve. If you have the robot geometry, you can just figure out where a particular coordinate system is going to be. And then we saw how the inverse kinematics in the Robotics System Toolbox lets you use an iterative solver to figure out these joint positions given a specified position. And we were able to design all these algorithms by commanding that position of the robot. The next step is then to consider dynamics. And this has to do with given the angular or the displacement positions of your robot joints, what are the necessary forces and torques to make that happen? The additional information you need there is in addition to just the geometry of the robot, you now need to know things like the masses, the moments of inertia, and so on. And that's what we're going to dig into.
Sebastian, and in order to obtain those masses and moments of inertia, can you have some suggestions for that?
Yeah, so let me jump over to the software really quickly. So what I ended up doing to get these masses is I found the Onshape CAD model for this robot arm. And what you can do in most CAD platforms is you can assign materials to these things. So for example, we know that this robot is 3D printed, so we pick a material that is related to that. And what you can do in most tools, like if you select a particular, you know, body or rigid link in your robot, you can open up these little measurement properties, and then this gives you things like the mass, the center of mass, and the moments that are needed for those parts. When you go into MATLAB, when you define that rigid body tree, as you saw that we can basically define our manipulator by importing its geometry into MATLAB. Now we can also add its inertial properties. To do that, I've used a script that basically grabs all these values from that CAD model I showed you, and it assigns them for each of the rigid bodies that make up this robot. So you see each body here has its own mass and 6 elements of inertia. That is the 3 moments of inertia and the 3 products of inertia that define the off-diagonal terms. So once we have this is when we can start solving the inverse dynamics for the robot. So we have that, but then the part that we're still missing is how do we actually assign these forces and torques? And to do that, you need controls, and that's really the main focus of this video. You have your manipulator, you have your desired motion, and you have your actual measured motion of the robot. Uh, Now, there's lots of different ways to design your controller, but generally they kind of get broken down into this feed forward and feedback elements. Feedback is probably the one that is most common in all controllers. It's where, you take the difference or the error between your desired or reference motion and your measured, and then you try to do something to correct that. In our case, it would be to apply torques. So I think, the most naive way to do a control of this arm would be to just take each individual joint and then have, six separate PID controllers for them. But there's other ways to tackle this as well.
Sebastian, so in this particular control block, what are we expecting to see in different robots?
This is kind of where simulation is the key thing, which is why we're discussing it. With simulation, it's pretty easy to just experiment with different controller architectures. So, you can try controllers that have only feedback or feedback and feed forward. You can have different types of controllers for each of these, and all in a safe environment. We'll show you two different types of controllers just as a taste of the kind of experimentation that you can do. One thing to note on the feed forward side, there's a couple ways to do that as well. So what feed forward means is that you're not using any measurements, but you're still using that to apply your control. There's a couple ways to do this. The main one that we're going to talk about is 'cause we have knowledge of the model of the robot, right? We have all its geometry, we have its masses, we have its moments of inertia. So we can figure out things completely independent of measurements. Like if you want your arm to stand up against gravity, then you already know that you're constantly going to have to overcome that. And you don't need a measurement for that necessarily. Same thing, like if you're trying to get to a certain position, maybe you can use some of that information to help guide your input torques to be better. I guess one more note on that, like the feed forward doesn't have to use a model of the robot. You could also just have, feed forward gains and design your own thing. So just leaving it at that there. I think we should just jump right into the software.
Sounds good. Let's take a look at the software right now.
All right. So revisiting the models from the previous section, we're going to start with this waypoint tracking model. And if you've watched the previous video, you might see this as familiar. So we had this state float chart that actually dictated all our waypoint following logic, and we haven't really changed anything here. What's different in these files is now if you see that the bottom of the model, you have three different actuator types to explore. So you have your ideal motion actuation, where you give the arm positions and it just goes there. And then we also have two different types of controllers that we're going to be exploring. So I've already run the motion actuation simulation. If I rerun it for you, you'll see that the robot is able to pick up this ball, move it around a trajectory, and finally drop it off at the end. And again, all with perfect actuation. So if we now add torque or force actuation to this robot, I'm just going to switch this over to use this configuration space torque model.
Sebastian, and these clickable links that you have in the bottom, what are they doing in the model to be exact?
Yeah, that's a good point. So these are actually setting up different variants. So the block that's at the bottom of this model, which is, our basically our simulation model, depending on which of those three links you click, it will change the implementation underneath. So we're going to jump now into the kind of the differences between uh, these blocks, right? The model underneath, you see that there's, like I said, three different subsystems, and we've just selected the first torque actuated block, and we label this one as using a configuration space controller. We'll talk about that. So if we go into this block, you'll basically see it contains our robot simulation model as well as the environment model, but then it's also got some of the control components around it. This is labeled as a configuration space controller. What that means is that the controller already accepts the joint angles as its reference input. What that means is that you first have to solve the inverse kinematics because you're giving the robot an XYZ target position and you have to convert that to joints. So using the outputs of the inverse kinematics, you then do the control and then you pass that into the actual robot. Let's look into the joint controller.
Sebastian, and the output of this controller is going to be torques, right? Not position anymore.
Exactly. So it's going to be the four torques of the angular joints and then the two forces on the grippers. Yeah, so if we take a look at this controller, basically there's two primary components that we've highlighted here. So you have the inverse dynamics, which is doing the feed forward part. And you see these are new blocks in the 2018A release, by the way, where once you've defined your rigid body tree for your robot, you can pass that into Simulink and it will do all these common tasks like, inverse
Right.
dynamics, forward kinematics, and so on. So again, our feed forward part is using inverse dynamics. It's saying with knowledge of the geometry and the dynamics of the robot, if I have a target configuration, velocity, and acceleration, then give me the necessary torques and forces. And then at the bottom, we have a PID compensator that picks up the slack. What this helps you account for are things like disturbances, whether it be, sensor noise or external disturbances, but also things that are not accounted for in the rigid body tree model. For example, if your joints have damping on them. So it's always good to have some kind of feedback in any of your models.
Okay,
Like,
Sebastian, and I noticed that the inverse dynamics block, it takes in the robot configuration, the joint velocities, and the joint accelerations. And you've used a derivative here. Is there any other situation in which you might do something different?
yeah, in fact, I guess I would encourage all of you out there to do something different. The way that inverse dynamics works, because you're computing forces and torques, then like passing it into position is not enough. You have to also tell it at what velocity and what acceleration it should be in. So what we did here, as you just said, Jose, is we're using a discrete derivative to approximate this given our position measurements, which is very susceptible to noise. There are ways to improve on this. For example, if you're doing a kind of curve or spline-based trajectory, then you already have a parameterized curve for your position over time. And these curves are designed to have analytical derivatives. So what would make this a lot smoother is if you had these curves, you would then also have expressions for the first and second derivatives and pass these directly
I
into
see.
the blocks.
So basically, the more information you have about the task you want to complete, you should be able to, instead of directly derive this, you should be able to provide separate individual signals, right?
Exactly.
Mhm.
In fact, derivatives is one, but maybe another one that you could use is if you actually have velocity measurements in your joints, that would help as
Oh, I
well.
see.
Yeah. The way that we've gone around it here, if you see these blue boxes in the controller, is that we've decided to filter with just basic low-pass filters the input and output so that we're actually smoothing out the motion. And we found that that helped a lot. So, yeah, last thing, just to dig into the feedback control really quick, you see that here I basically just have 6 PID controller blocks. There's going to be 4 proportional derivative controllers for the 4 angular or rotational joints, and then 2 proportional integral controllers that manage the gripper. So I've got the simulation that already ran. I'll just rerun it for you. And at a first glance, you can't really see the differences between the motion and the torque simulation. However, you can always do like run comparisons in Simulink. What we're interested in is now that we have this torque controller, can we actually look at the torque that was needed to make this motion happen? So to do that, I'll open up our simulation data inspector here. And I'm just going to configure it really quickly to display what I call the joint input signal. So this contains basically the 6 inputs to the joints. So you have the 4 torques for the 4 rotational joints, and again, the 2 gripper signals there. So you'll see, for example, that because of the filters, this signal is relatively smooth, except you've got these, kind of big jagged edges. And this has to do because of how we do the waypoint tracking. We're actually just sequentially going from one waypoint to the next. And every time you immediately jump from one waypoint to the other, you get this big spike in torque. So, I invite everyone to create smoother planning, or if you're interested in seeing videos where we talk more about, motion planning for manipulation, that'd be really interesting to hear.
Cool, Sebastian. And basically, with these plots, I would be able to go back and look at my motor specs and then decide whether, this controller is going to work in my system or not, right?
Yeah, and that's a very good point. So if we just do a quick glance, I'm just going to put in the cursors here. For example, you'll see that I guess the biggest torque that we're seeing in this motion is something like 1.3 Newton meters. So yeah, like you said, it's a good benchmark to see, can your motor provide this torque at that speed? Do you have to, pick a different gear ratio for your actuators? Do you maybe need a different motor? So yeah, I think all of this will certainly help you with design. If you remember, we had another example that had to do with ball tracking. So this is a different motion that used the same kind of control, namely the inverse kinematics, but it used a different supervisory logic. So instead of tracking waypoints now, it was looking at the position of a ball over time and actually grabbing it off of the air. So what I'll do is I'm going to switch to the third controller type here, which is the task space controller, and I'll run the model. Okay, so we've slowed down the simulation. You see the ball's in the air and the robot is able to catch it. Um, so this was a task that we had proven in the previous video with motion actuation, but now we've done it also with torque. So I'll just replay that. Okay. If I go back to the model, you see that for this one, if you recall, you could double click the block here and you could change your initial position, heading, and even whether the ball is airborne or just rolls on the ground. So I invite you to try break this controller. I bet it's pretty doable. Uh, More importantly, I invite you to try and make it more robust. Um, so why don't we dig into this new controller that we chose, which is the task space controller.
Sebastian, and what would be the major difference between the task space controller and the configuration space controller?
So task space here denotes that we're doing the control directly on the Cartesian or the XYZ position of the gripper.
Uh,
This means that we don't need to solve inverse kinematics here. The way that we do inverse kinematics in the robotic system toolbox is it's all using an optimization algorithm, which means that it's an iterative solver that can take some time to converge. It could also
Right.
not converge depending on the inputs you give it or the initial conditions. So this completely gets around that, which could potentially give you a boost in speed. Maybe you could instead implement your own analytical inverse kinematics that instead of using optimization, you just have the equations that would solve it. But that's on the robot designer to see if that's possible.
So I think in the previous demo we were using the inverse kinematics, so we had to keep an eye out for the number of iterations that it went
Yeah,
through, right?
exactly. So in this
Hmm.
case, we're doing something completely different without any need for iterations. Let's
Hmm.
explore how we did that then. If we go into the task space controller, you see that this controller structure looks a lot different. Everything that I've just highlighted at the bottom here is actually the same from the other controller, and that's because we've decoupled the gripper control from the other four joints. But the interesting part that we're going to focus on is, how do we control those four revolute joints? We, pass in the reference end effector position, XYZ, and we compare it against the actual measured position of the end effector, run it through a PID controller, and then that gives us basically an equivalent force to apply to the end effector. But then that still leaves us a question. So how do we convert from the end effector or the Cartesian space to the actual joints? And that uses the notion of Jacobian. If I double click this block, you see there's that we provide a block for it. The basic or the definition of the Jacobian here is it's basically a mapping from the velocities in Cartesian space, so x, y, z, and angular speeds, to the actual velocities of the joints. So it gives you a way to do the control basically in the task space, and then you can multiply that output by the Jacobian and then get basically torques that you can pass into your manipulator. And this is what really replaces the inverse kinematics.
Quick question, Sebastian. So if I'm correct, you should be able to take into account the X, Y, and Z positions of the end effector and the X, Y, and Z orientations
Yeah.
of the end effector. So how does the controller account for those?
If you notice what gets passed into the matrix multiplication, we're
Hmm.
actually chaining the output of the PID controller with a bunch of zeros. So in this case, we're saying we don't care about orientation, but you might.
Okay.
So you could replace this also with some kind of controller behavior that would also similarly try to set the orientation of your end effector. And then all of that again gets converted to the whatever torques and forces are needed on the joint space. The last thing to note is that we still have a feed forward component to this controller, which is this gravity torque block. So like regardless of the rest of the controller, we're also whatever output we get from the PID with the Jacobian, we're also summing up the torque needed to compensate for gravity. And we find that's very useful because otherwise, basically to overcome that gravitational acceleration, your PID controller would have to be tuned differently, and it would depend heavily on where you are. So this kind of decouples the gravity from the tracking portion of the controller.
Sebastian, and these control algorithms seem like they're fairly complex. And how did you go about, implementing them and trying them out before you put them in the actual robot model and make them implement tasks and things like that?
Yeah, that's a very good question because yeah, we definitely didn't just get to this point, right? In fact, these plots are magical to see, I would say. The fact
Okay.
that we can see these torques these joint inputs becoming stable is a product of having tested these controllers on their own first, and that's something that you should definitely do as well. So as part of the updated file exchange submission for this, we have provided a couple of test models that you can use. There's namely the torque control in configuration space test model and the task space. So I'll just open up one of these and show you what we mean. Basically, to check whether your robot arm can move to a particular point, you don't need to put it in this waypoint tracking or this ball tracking framework, right? All you need to do is give it some kind of reference input and see if it follows that. So this model has a couple of, sinusoidal inputs for the joint angles, and this lets you test the controller to see if it behaves properly. And you see I've got some measurements on the right as well, which we can just use to validate whether this worked. So for instance, what I would recommend is, can your robot respond to joint commands that let it explore its full space? So you see this robot is snaking around, it closes its gripper, and you kind of want to verify this first before you put it into your planning. Um, so if I plot, for example, the joint angles versus their actual measured values, you see that there's a little bit of a delay between the reference and the actual, but overall the tracking is pretty good.
Right.
And of course, by simplifying the model, it also lets you use some of our control design tools that are available in Simulink. So if I go really quickly to, one of the proportional derivative compensators in this model, if I click the PID block, there's the little tune button. And what that's going to do is it's going to linearize my plan or give me a linear approximate of the robot model about a certain point. And then it lets me, if I want, to tweak the control parameters. So you see here, I can start playing with these sliders um, and see if I can, design a better controller and then try resimulate it. So anyone who's interested in this kind of stuff, we have a lot of tools for control design, including the PID tuner. We'd be happy to talk to you more about it if you reach out to us. So I think that's an overview of everything we've done. We invite you to download the entry off of File Exchange. We've also provided the link below.
Yep, definitely give us some comments on those files. And if you can break the controllers, please fix it and forward the fix as well. Okay, Sebastian, thank you very much for showing us all of those inverse dynamics tricks. Why don't you walk us through a couple of key takeaways from what we went through today?
Sure. I got 4 points here. I think that the first two just have to do with learning the language of manipulation. Knowing what kinematics is versus what dynamics is an important thing. So again, kinematics has to do with only the robot geometry. How do you map between the joint positions and the actual location of like an interesting coordinate frame in your robot, usually the gripper? If you're already using like a pre-made robot, chances are that the manufacturer has already provided their own controllers under the hood, and you only need to care about kinematics. However, if you have access to torque control on your manipulator or you're designing your own, then you also need to worry about the dynamics. So how do you find the necessary joint torques and forces to achieve certain positions? And that's what we've covered in this video primarily. We talked a lot about simulation. So the fact that we are able to import robot geometries into MATLAB and Simulink lets you experiment with lots of different controller architectures. So we showed you, the configuration space versus the task space controller. There's lots more you can try. So we're hoping that these tools give you a canvas for, if you read a paper, you can try implement the controller in Simulink and see if it works with your robot, as well as
Right.
with parameters. So you can do a lot of, controller tuning. You can even do optimization with these models and try to automatically tune your values. And the final thing is deployment. These controllers that we designed, both the supervisory logic and the controllers themselves, you can generate code from these, or C or C++ code, which you can use to target hardware or target other software frameworks like Robot Operating System. So, there's a lot of exciting stuff you can do with all of this work, and we hope that you try some of it out.
And if you guys do try Simulink to control some of your robots, it will be really cool to hear back from you guys some of your experiences as well. Okay, guys, I think that's about all we have for you today. As always, if you want to contact us, please reach out to us by email or our Facebook group, and make sure to check out some of the other videos that we have in the robotics arena. Thank
Awesome.
you. Have a good one.
Yeah, thanks. Bye.